Screen is visible to everyone?
Yes, screen is visible.
Any lagging is there? Or
No, we can see your slides.
okay. So just now what we have seen is that how this quantum teleportation protocol works, in which the state of this Alice qubit psi is teleported to Bob at the end of the protocol. So we will see how this is happening or whether it will happen or not. So with this specific gates combination and this M1 M2 transfer and applying X and Z gate, we are claiming that this thing will give psi, that is nothing but alpha times 0 plus beta time 1. So okay, so we can divide this in different stages. So these horizontal lines, every time remember this, these are basically qubits. So at this point, what we are saying is that the first qubit q1, second qubit q2 and q3. So what we are saying is that this first qubit is psi state, and second and third are denoted by beta 00. That is our initial state. That is okay. Now we are just writing the derivation of this beta 00. So beta 00, if you remember, it is nothing but 00 plus 11 by root 2. So we have just replaced beta 00 with this thing. Now see, what we are doing is we are applying, or maybe just we are just expanding this thing. So beta 00 we replaced, and psi we know it is nothing but alpha times 0 plus beta time 1. So what we did is psi's value we have put and beta 00 value we have put here, and we are just multiplying it. So on the multiplication we are getting this kind of states. How we are multiplying is this alpha times 0 is multiplied with the entire thing, then beta times 1 is multiplied with the entire thing. So alpha 0 time multiplied with this, beta 1 is multiplied with this. So this is our 0, just we are expanding it. So on expansion we are having this psi 0 as an state. Now what we are saying is that we are applying control NOT gate from qubit 1 to qubit 2. This is the gate we are referring. This gate is basically doing the control NOT operation from q1 to q2. So how it will change? Whenever this q1 is 1, it will change the q2 qubit. Okay, as we remember from the control NOT gate working. So whenever this control qubit q1 is 1, it will change the other qubit or flip it. If it is 0, then both will remain same. So it is applicable whenever this control or this first qubit is 1, then only it will flip the other qubit. So just remember by that working. So see here, this is your first qubit. So it is 0, so it will not change anything. They will remain same. See here, first qubit is 1, so it is going to change the second qubit. Second qubit is which one? So if you remember the naming here, this is first qubit, second qubit, third qubit, second, third, first, second, third, second, third. So in this case, first qubit is 0, so they will remain same. In this case, first qubit is 1, so it will change the second qubit. Second qubit is this one, so this will become 1. Same way, since it is 1, first qubit is 1, so second qubit will be flipped. So second qubit is flipped and it has become 0. So since this gate is applied from first qubit to second qubit, so it is nothing to do with the third qubit. And you know that third qubit is with Bob. This Q3 is with Bob. So Alice cannot perform anything on this Q3. Q3 will remain same till Bob applies something on it. So Alice has applied control NOT gate from first qubit to second qubit, and both of this Q1 and Q2 are in her possession. Now on this application of C0, she get psi 1. Okay, psi 1 state. So at this point we have come, psi 1 we have derived. Now what we are doing is Alice is applying first qubit Hadamard gate. So see here, she is applying Hadamard gate on the first qubit. So if you remember from this Hadamard gate operation, so Hadamard of 0 is nothing but 0 plus 1 by root 2, and if it is applied on one state, then there will be a negative sign. Okay, just apply it on first qubit. So here this qubit is 0, so it will become 0 plus 1 by root 2. So root 2 we are multiplying it, so it become 1 by 2. Similarly here also it will become 0 minus 1. So see, we have done nothing, just apply the Hadamard gate on the first qubit. In this case it was 0, so it became 0 plus 1. In this case it was 1, so it becomes 0 minus 1. And 1 by root 2 we have taken out and multiply with this already 1 by root 2, so it became 1 by 2. So now we have got the psi 2 state. Okay, psi 2 is what? Here. Psi 2 we have derived, and what we are doing is we are just trying to rearrange the terms and just multiplying and rearranging. So psi 2 we are having this state. So what we are doing is we are multiplying this 0 with the other thing, then 1 with the other thing, and similarly here 0 we are multiplying with the entire thing, and this 1 with entire thing. So just see here, 0 we multiply with this state 0 0 and 1 1, 1 we multiply with the 0 0 and 1 1 likewise. So now what we are having is this kind of expansion we are doing with the multiplication. And now just what we did is we have multiplied this 0 with this other thing, so it becomes 000, so it becomes 011. Likewise we multiply 1 with 00, it becomes 100, and same way we multiplied it, so we get psi 2 like this. Now what we are trying to do is just multiplying with this alpha also. So alpha we are taking inside, so alpha times 000, alpha times 001. So just we multiply and we get separate terms. Now we are trying to rearrange, okay, and we want to make sure that the first two qubits are same or similar. So wherever first two qubits are similar, we are just combining those two terms. So see here, in this case first two are 00 here, and if you see here also we are having 00. So with these two terms we are bringing together, so it is alpha times 000 plus beta times 001. So why we are doing it? We just want to bring in the terms which are same for first two qubits, q1 and q2. See here, just remember it is first qubit, second qubit, and third qubit. So what we want is that first and second qubits are same. We want to just bring together. So here 00, there 00. Same way we bring in two terms which first two qubits are 0101. We uh, take them together. Likewise 1010 is at same time. It is we are combining them, then we are 11 we are taking together. Now what we are doing is just taking the 00 or the whatever the first two qubits are common here. So here the common term is 00, so we are taking that out. Here if you remember or see, here 01 first two qubits 0101 are same, so we are just taking that out. And likewise 10 and 1. So what we did is we just did the multiplication, we just this some rearrangement, and we try to take the first two qubits outside, and whenever they are same, so in these two terms they are 00, in these two terms they are 01, and likewise. So we get this kind of psi 2 state. So psi 2 is this one. So just we rearrange and just take some multiplication and then common, so we get this kind of state. So we are just writing it like this, so we get this kind of psi 2. Okay, now what we are saying is we are going to measure the first two qubits. Okay, first two qubits we are going to measure. Okay, so on measurement what you will have some classical bits. So see here, this is first q1 q2 and this is q3, q1 q2 and this is q3. So if you forget about this thing, just focus on the first term here. First term, if you focus, if I measure this first two qubit as a q1 and q2 as 00, because in this case first two qubits are q1 and q2 are 00. So suppose I measure the first two qubits and I observe as a 00, then what is q3? Q3 is alpha times 0 plus beta times 1, and it is nothing but what? It was the psi which was with Alice. See here, the qubit 3 is nothing but alpha times 0 plus beta times 1, which was with the Alice in the beginning. See here, alpha psi was nothing but alpha times 0 plus beta times 1. And at the end of the protocol, here what we are saying is, suppose this Alice measures 00, then what we are saying is you need not to apply anything. Psi 3 has become psi only. See, whenever these two are 0 0, so x power 0 is 1, x z power 0 is 1, basically identity, so you don't apply any gate. And it has already, q3 has already become psi, that is alpha times 0 plus beta times 1. Are you able to understand this thing, friends? So suppose if we measure first two qubits at 0 0, then the qubit 3 in itself is psi. This q3 is nothing but psi only. But you may say that maybe we can observe 0 1, or maybe we can observe 1 0 or 1 1. So these all measurements of q1 and q2 0 0 0 1 1 0 1 1 are equal likely. So probability of measuring m1 m2 as 0 0 or 0 1 or 1 0 or 1 1 is what? Is 1 by 2 mod square, because the amplitude of these states are 1 by 2 for every state. So 1 by 2 square is nothing but 1 by 4, that is 25%. So 25% chances are there that on measurement of this psi2 state, if you measure the first two qubits, then you may observe 0 0, you may observe 0 1 with 25% probability, and you may observe 1 0 and 1 1 with 25% probability. Suppose if you run this experiment or the circuit 1000 times, then almost 250 times you will get 0 0, almost 250 times you will get 0 1, and likewise. So what will happen in this case? If this q1 and q2 are 0 0, then simple, we observe the, or we teleported psi from Alice to Bob. So we did not do anything on q3. But if you see in the other expression, see here, it is not equal to psi. So remember, psi is what? Psi is alpha times 0 plus beta times 1. So see here, if I observe q2, q1 and q2 as 0 1, then I am not having psi here. What I am having is alpha times 1 beta times 0. Suppose if I change these coefficients 1 and 0 to 0 and 1, then what is, I will have psi. So what we are trying to say here is that if we apply x gate, if you observe 1, then what we are getting here is on q3. On q3 we are getting this alpha times 1 plus beta times 1. And suppose if I apply x gate, remember, if I apply x gate on it, x gate on this state, so then this 1 will become 0, and this 0 1 will become 0 will become 1. So just we apply the x gate on the q3, then applying this thing, we are getting alpha times 0 plus beta times 1, that is nothing but psi. Suppose if we observe 1 0, see here, then what is our state inside? It is alpha times 0 minus beta times 1. It is almost psi only, just this sign is the problem. And you remember from the previous z gate operations, what does z does? Z changes the sign of one state. So if I apply z gate on this state, so 0 will remain same, but this 1 will become minus 1. So minus minus, it will become plus. So what we will have here is alpha times 0 plus beta times 1 on application of this z gate. That is nothing but psi. Suppose if we observe this thing as a 1 1, because these all are equal likely, 0 0 0 1 1 0 or 1 1, all are equal likely. So suppose if we observe 1 1, in that case q3 was what? This is your q3, and you want to make it as a psi. How we can make it as a psi? If we apply these two gates x and z in this order. So first we apply x gate, then what it will become? This 1 will become 0, this 0 1 will become 1. So it has now become alpha times 0 minus beta times 1 on application of this x gate. So still it is not psi because of this sign. So this can be resolved by applying z gate. So when you apply the z gate, this minus sign will go, because So, and it is nothing but psi only. So what we have seen during this derivation is that we observe psi2 as this, and on psi2, if we apply the measurement gate, okay, m1 and m2, so we may get 0, 0, 0, 1, 1, 0, and 1, 1 with 25% probability each. So if both of m1 and m2 are 0, 0, then we did not apply any gate. We are basically having psi3 on psi on q3. Q3 qubit has become psi. If it is 0, 1 or 1, 0, then we need to apply X and Z gate. And if it is 1, 1, then we need to apply both X and Z gate. Then it will convert that Q3 into psi state. So see here. So these are 4 cases. And application, there is nothing to be done when it is 0, 0. Whenever it is M2 is 1, then you need to apply X gate. When M1 is 1, you need to apply Z gate. And when both of them are 1, then you need to apply X and Z gate. So remember, you need to apply X gate before Z gate here. You cannot do it in other order. Why? Because you remember, see here, if you do this Z gate before applying this thing, so if you apply Z gate on this, then it will become what? It will become plus. Oh, sorry, it will become minus. So 1 will become minus 1. So it will be minus alpha time 1 and minus beta time 0. Now you apply X gate on it, then this will become 0. So it will be become alpha times 0. So negative sign will be there, minus beta times 1. So it is nothing but minus of psi. So if you apply the gate in other order, if you apply Z first, then it become minus psi. So you need to make sure or be cautious while applying this X and Z gate. If you apply X first and then Z, then you will get psi. Otherwise, you will get minus psi that we have seen here. So this way, we can create teleportation circuit. And what we have seen here is that if Alice has this psi and q2 part with her, apply these gate operations, then measure them, and this transfer this m1 and m2 bit value. So what happens is that this bit value m1 and m2, Alice needs to transport on classical channel. Means classically she need to transfer these 2 bits. So if you transfer the 2 bits classically, then it cannot travel faster than light. So the information transfer will be always restricted by the speed of light here. Why? Because until and unless Bob does not get this m1 and m2, he cannot apply X and Z. He does not know how to whether to apply X or whether to apply Z or not. Depending upon the value m1 m2 received, he will apply X and Z gate. So this has become generic. If m1 and m2 are 0, 0, then nothing will be applied. Identity, this gate becomes identity. Whenever their values are 1, they will be applied 1 times. And this way, all 4 cases of m1, m2 values are taken care. So if this thing is generic, whatever the value of m1, m2, it will cater for them. And accordingly, apply these gates and you will get the psi state on the receiver side at Bob. So what are the key takeaways here? Any question is there so far? Any questions?
Yes, sir. Yes,
Yeah, please.
yes. So, should I dictate, sir?
Yeah, please, because I am in full screen mode on this slide only.
Okay.
So whatever question you find useful, you can tell me.
Yes, so my student is dictating.
Yeah. Hello.
So, question is, what exactly measures?
Just a second. I think there is audio issue. My voice is clear to everyone?
Yes, we can hear you.
Yeah. So let me read out chat myself. Okay. Can I read? Yeah. Just a second. So okay. So I will take from this thing. Yeah. So the question by Hemani Koshal, that is it correct to say Hadamard and C0 plus measurement? So yes, we are doing the same thing, and then we are measuring the Alice's qubits to classical bits. So that's correct. Yeah. So the question by Bhavna: how do we separate Bob circuit and Alice circuit in terms of transmitter and receiver in terms of how entangled bits are shared? So see here in the circuit here. So physically this psi can be realized by a photon. So that is with Alice. This beta 00 is basically an entangled state. It has been shared. So these two qubits are there, Q2 and Q3. These also a photons. So what beta 00 is basically Q2 plus Q3. These two photons are there. So Alice is having first state Q1 as a photon and second qubit Q2 as a photon. So it will have two photons with her, and this entire thing is at Alice side. Yeah, so entire thing is with Alice. Cut it like this. So this entire thing on with Alice, and the lower side is with Bob. So the circuit is with so circuit remains. Alice is having these photons with him or with her, and she is applying this operation. And since she is measuring, what it is doing is, so you can just, yeah. And Bob is what doing is, Bob is having only Q3 photons. So on Q3 photon, he is applying this operation. So the circuitry maybe we are showing in one slide, but they are, this part is separating them. So these things are applied at Alice side, these things are done at Bob side. So they are separable. Whether the first two qubits are classical bits? No. The first two qubits are qubits only, quantum bits only, until they are measured at this state psi 3. So before this, they are quantum bits only, and they are measured at this end. So when you measure them, you will get M1 and M2, two classical bits, and which are denoted by double lines. Okay. So you can see here, the double lines are showing the classical bits. So now these two M1 and M2 become classical. Okay. Before the measurement at this point, they are quantum bits. What is exactly does Bob measure? Q3, which is entangled qubit? Yes. So Bob is measuring the qubit after applying these two operations, X and Z gate. Bob is measuring, and on measurement, Bob is observing that it has psi state. Okay, any other question is there?
No, sir. I think no.
Yeah.
Yes.
So just I am recapping you, and then we will be seeing the Qiskit implementation of this thing. So see here what we have done so far in this is, so because we need to remember this thing when we will be see the circuit. Yeah. So what we will be doing is, with this help of this entangled pair of qubits Q2 and Q3, we are able to transfer the state of qubit 1 to Bob. And in between, we are doing this gate operations at Alice side and measurement. And at the Bob side, we are doing these gate operations. And at the end, what we are observing here is that psi is the third qubit Q3 is becomes psi, and that is nothing but alpha times 0 plus beta time 1. Okay. So let's see this thing with Qiskit. So before going to Qiskit, I want to tell that what is Qiskit is. Qiskit is nothing but a platform or a framework wherein you can create quantum circuits, and you can do many more things. Not only create quantum circuit, you can simulate them on classical computers using quantum simulators, and you can run those quantum circuits or quantum programs on actual quantum computer as well. And this Qiskit frameworks provide you many more things, features which you can use for your quantum application development. So here what we are doing is, as you know that already we have seen that thing, IBM Composer, wherein what you observe that you can do these things graphically. So maybe if you remember, in Composer, what we have is we have these kind of gates available to us. We are given these qubits and we can apply different gates simply by dragging and dropping those gates, and we can implement our quantum programs or quantum circuits. But the limitation here is what? For a larger application, you cannot do at this kind of gate level things. You need high level programming interface wherein with some line of codes you will be able to generate the circuits. Suppose if I want to measure here this 2 qubits, so I need to drop this measurement operation 2 times like this. Okay, so this thing is tedious, not elegant way to do. So if we have some kind of programming interface wherein we can do it with Python kind of programming interface that Qiskit provides, you can do those things elegantly. So we can see the things on Qiskit. So before going to that, I can tell you, I can show you how we in Qiskit for the bare state. Then we will see the quantum teleportation. So we are just importing some quantum libraries. Okay, so for that Qiskit, you need to install the Qiskit on your local machine, and then you can use any Python tool wherein you can run this kind of Python files. So I am using this which is called Visual Studio Code tool, which you can use, or many other tools are there which you can use. So just you need to install the Python and Qiskit libraries, and then you are ready to go. So first part what we are doing is we are importing the Qiskit libraries and these other libraries. One is for visualization, so to plot histograms of the states, and we are using the air simulator. So we are importing those files. Now what we are doing with this QR quantum register. So what we are doing is with this instruction we are creating a quantum register of 2 length. What it means? It means that register will be having 2 qubits, Q0 and Q1. This one line is doing the job there. Otherwise, if you remember from the composer, you need to add qubits here. You need to add qubits. You need to add qubits for this thing. In this Qiskit, you simply write quantum register of this length. So then it will create accordingly. Same way, to measure those quantum registers, you require classical registers or same number of classical bits. So we are creating a classical register of length 2 here. Why? Because we are just seeing that quantum entanglement or Bell state circuit generation, which we have done using a GUI based composer. Same trying to implement here with Qiskit. And just we are creating a circuit with this quantum register and classical registers. So, and now we are drawing it. Okay, so it is drawing it for us, and there is better other way to draw it with the MPL library. So when you draw it, it will look like this. Just let me rerun it. Yeah. Now what we are doing is, so just we have 2 qubits and we are applying. We are having 2 classical. Let me just clear it and run it. Yeah. So what we are having is we are having a registers Q2 with 0 and 1 qubit and 2 classical bits. Now what we are doing is we are applying Hadamard on which qubit? First qubit. So quantum register of 0 means first qubit we are applying Hadamard gate, and then this CX is nothing but control NOT gate. From which to which qubit? From first qubit to second qubit. We are applying the control NOT gate and just drawing the circuit, how it looks like. So first qubit we apply Hadamard gate, and second qubit to second we are applying control NOT from first to second qubit. Then we are putting measurement operations. So just this line from quantum register to classical register, it will put measurement from all quantum bits to all classical bits. So one line will do the things. Otherwise, if you remember, if you do it in a composer, you need to put that many measurement operator. How many qubits are there? So if there are 4 qubits, then you need to put this measurement 4 times here. Okay, so that thing is done here in one line. Circuit dot measure from quantum register to classical register. So it will put according to the desired instruction, it will put the measurement operation. So if you remember from the previous first sessions thing, that with this Hadamard and control node we can create Bell state that is nothing but 00 plus 11 by root 2. So basically we require this thing for teleportation as well. So we are just recapping that how we can create Bell state such as 00 plus 11 by root 2 in Qiskit. And now we are running this thing on AR simulator. So basically we do not have access to actual quantum computers, so we can simulate those things on classical machine as well. Okay, and for that we can have this air simulator which is local to our machine, so that will be running on laptop only. But if you want to run this on actual IBM device, then you can run it. Just you need some instruction here, so that this code will be uploaded to the IBM's cloud, and it will be run on IBM's quantum computer, and you will get the result back. Now just printing it, and just we are transpiling it. Transpiling is here is not required, but when you run this on actual quantum computers, the circuit is mapped according to the qubit topologies of actual quantum computer, and just we are running it 1000 times. Okay, and we are printing the results and printing the histograms. So what we are expecting is that this kind of state, if we run the quantum circuit 1000 times, what we are expecting, that almost 500 times we will get 00 state, and 500 times we will be getting 11 state. So just run it again. So if you run it again, then here this time what we are getting, 491 time we get this thing, and 409 we get this thing. So if you again run it, then maybe we can get 510 this time and 590 this time. Okay, so these things are probabilistic, so probability is almost 50-50 if you see in all the example. And if you increase the shorts or this from 1000 to 10,000, then probability almost 50-50. So with this we can create this kind of Bell state, and if you want to run an actual quantum device, then you just need to put your accounts detail and you can run it. Okay, so this we are able to create which is state, Bell state. And if you want to create a Bell state which we have shown earlier, in which we are initializing the first 2 qubits by 1 1, then we are getting another states. So just put those instruction circuit.x on Q0, again the same thing you put on Q1, circuit.x on Q1. Yeah, so what we are doing is we are applying NOT gate on first and second qubit. So what it does is it will make the first and second qubit as 1 1. So if you remember from that slide, so this kind of Bell state you want to create, which is 0 1 minus 1 0 by root 2. So we are just need to initialize first this 2 qubits to 1 1 state instead of 0 0. So we apply 2 NOT gate, and then we created a circuit. So just clear all outputs and run it again. So circuit dot Q0. So the name is QR, not Q. Quantum registers. Yeah. So this circuit dot X QR of 1 means on second qubit you are applying X gate of the circuit. Clear all outputs and run again. So what we did is just we initialize them with 1 1 and then applying Hadamard and NOT gate. So if you see the results, in that we are expecting that the states will be 0 1 or 1 0, opposite to each other. So if one get 1, then other will be 0. There are 2 qubits, so these 2 qubits will be opposite of each other. If we will get 0 1 or 1 0, in both the cases they are opposite to each other. So with this circuit we can create entangled Bell state pairs, and that is a prerequisite for quantum teleportation circuit. If you remember from here, yeah, so remember from here, what we require in the beginning is that this 2 qubits Q2 and Q3, we want them into Bell state pair. Okay, So with that program which I have shown here, we can create this kind of bell pair, and we can have this psi as, so psi can be 0, so psi can be 1. So just what we are doing here is that initially we initializing psi with 0, and we want to see here that whether we are getting 0 or not. And second time we will do psi initialize with 1, then we will see that whether we are getting 1 or not at this end. So we are taking the first example, let's psi be 0, and we are implementing our quantum circuit for teleportation. So just see here, we just require those initialization or import libraries. Then we are initializing the quantum register with length 3. Why well length 3? Because we require 3 qubits. First qubit which the state we want to share or teleport, and second and third for entangled pair. So 3 qubits, and we are having the corresponding classical register of length 3. We created the circuit. Just remember from the example. Okay, so we have not done anything on the first qubit, so that means by default they are initialized with 0 only. Okay, now what is the part of your this thing? On the first qubit, h1 means second qubit, we are applying Hadamard gate, and from second to third we are applying control node gate. So what it will be doing is, it will be basically creating an entangled pair of state in qubit, second qubit and third qubit. So remember, second and third qubits are now entangled after this thing. So just see here. So what this statement are doing is, the second qubit and third qubit are entangled pair of qubit Bell state. Just Hadamard and this control node. So this part is done. So at this point, the second and third qubit are beta 0, 0. Okay. Now, as per the protocol, you need to apply control node from first qubit to second qubit and Hadamard on the first qubit. So this first and second qubit are with Alice. In the circuit, actually we are seeing them as a together thing, but in actual things, these things, second qubit will be with Bob far away, and these first 2 qubits are with Alice. So Alice is doing her operations. So this entangled is created, and now this second qubit is given to Alice. First qubit is already with Alice, and this third qubit is given to Bob. Okay, now Alice is applying some quantum gate operation control node and Hadamard on her first 2 qubits. So she is applying Hadamard, control node, and then this Hadamard, and then she will be measuring. So just see here, control node and then Hadamard. Then she is measuring her qubits. So what are those qubits? First 2 qubits. So first 2 qubits she is measuring. Now you remember, depending upon the values of this first and second qubit, you need to apply the Z and X gate. So what we are doing is, we are putting these 2 gates. So whenever the second qubit is 1, you need to apply NOT gate, or you are calling it as a, when this M2 qubit is 1, you need to apply NOT gate. So this gate does this thing. So it is nothing but, so you remember, whenever this control is 1, this qubit, this bit value is 1, then this NOT will be applied. Okay, this part, remember, whenever this second qubit M2 is 1, then X gate need to be applied. So that we have done here. So this second part is 1, second bit is 1, then apply NOT gate. And this is the blue color thing is nothing but control Z gate. So whenever this is 1, it will apply the Z gate on the last qubit. This part. Whenever this M1 is 1, then it will apply Z gate. Okay. So this is the thing happening here. And now what we are claiming is that at this end, if you measure this qubit, last qubit, it should be psi only. So you remember how we initialize this first qubit? We initialize with 0. So what we should observe at this second qubit? It should be 0 only. So when we are running it on air simulator, the results. So what we are doing is we are running it 1000 times. Okay, so 1000 times we are running it, and you see here this 000, it means the first qubit is 0, second qubit is 0, and this is a third qubit, that is 0. So what we required is third qubit should be 0. So see here, third qubit is 0. In this case also 1 0 0. Third qubit is 0. In this case also 0 1 0. Third qubit is 0. And in this case also 1 1 0 means third qubit is 0. So the first two qubits are 0 0 or 1 0 or 0 1 or 1 1. They can be any of these four possible combinations with 25% probability. But your last qubit is always 0. See here, last qubit is always 0, and that is the qubit we want to teleport. So see here, if you can see here, so these first two are basically nothing but M1 M2, that is being measured by Alice. The last one is the qubit outcome of third qubit, that is 0. See here, 0, here also 0, here also 0. So whatever the value of first two qubits, it can be any of those 0 0 0 1 1 0 1 1. The last qubit is always 0. That is, we wanted to teleport. Why? Because we initialize this qubit with 0. Suppose if we initialize the qubit with 1. So what this instruction will do? Circuit.x0. It will make the first qubit 1. Because initially the qubit is 0. So we are applying x gate on it. So it become 1. Now what we are expecting is 1 we want to teleport from this first qubit to third qubit. So just run it again. So we have make it 1. Okay. On measurement you see here, all the first two qubits, see here, first two qubits can be anything, 1 0 or maybe 1 1 or maybe 0 0 or 0 1. The third qubit, that is always 1. See here, it is 1 here, it is again 1 here. So whatever the choices of the first two qubits, but the last qubit is 1, which we wanted to teleport. See here, it is 1, again it is 1, again it is 1. Okay, so what we did is we initialize one time this qubit psi as 0, and we observe psi at the bob end 0. Again we did it psi initialized with 1, and then we observe 1 here. So if psi is any combination of 0 and 1, then we will have xi here. Okay, so if you run this experiment several times, maybe 10,000 times, still what should happen? We are doing it 10,000 times, and what we should observe is that this last qubit is this. It should always be 1. Okay, and see, we can run it again and we can see it. See here, last qubit is 1, last qubit is again 1, last qubit is 1 here, and last qubit is 1. The first two qubits are varying. They can be 0 1 1 0 1 1 or other choices, as we have seen in the derivation here. Just remember from here. So first two qubits can be 0 0 0 1 1 0 or 1 1. The last qubit Q3 is our interest of qubit, in which we want that whatever we are having in the initially at Q1, it should be at the Q3 at the end of the protocol. So initially at the beginning we are having Q1 as 1, and we at the final we are having Q3 as 1. So basically we successfully teleported the state 1 from qubit, first qubit to third qubit, or basically from Alice to Bob. So far any question is there? So I have done with this thing.
Yes, sir. You have few questions? Okay.
Yeah, I can take questions as many as we have sufficient time.
Yes.
Yeah, so I can read. Yeah.
Yes.
So okay, so I can take questions from timing. From I can start. Okay, so many questions are there. Just a second. Yeah, so let's begin from the last query. In teleportation, the state is destroyed and recreated at the destination. In cloning, the original state is supposed to be unchanged along with the creation of the clone, essentially 2 qubits of the same state. So the true. So what we are doing is at the Alice side, the qubit was there in the beginning at time t1, it was there, and once we measure it at Alice side, the qubit is no longer existing. The psi state is destroyed. But with the same information alpha and beta, it is recreated with the help of entanglement at Bob side at time t2. Yeah, I can share the code, no problem. So I will share both the codes, or tomorrow also we'll have some codes. So I will share everything with you. How recreating the qubits at Bob side is different from cloning. Okay. So if you remember from previous lecture, somewhere it was told that no cloning theorem is there. What it says is that you cannot create exact replica of a quantum state or a qubit. Means no cloning theorem prohibits you to recreate or make copies of a qubit, exact replica of a qubit. So that is still valid here. We are not cloning at all. What we are doing is we are saying that we are teleporting the state information, that is alpha and beta. So what we are doing is just this alpha and beta coefficients. The state is denoted by this alpha and beta only, and this alpha and beta are basically teleported here. Okay. And once the copy of this psi was here with Alice, once the Alice measure it, so psi is destroyed at Alice side. Then with the similar information, quantum information alpha and beta, it is created at Bob side with the help of this entangled pair qubit. Okay. So that's a different thing. Entanglement swapping and teleportation is different thing. In teleportation, our purpose is just to teleport a unknown quantum states information from one place to other. In entanglement swapping, we just want to increase the key distribution distances. So we do this with the help of entanglement swapping. So that maybe some session on QKD will be covering this thing. Yeah. So what does Bob measure? Bob measure the third qubit, that is part of the entanglement pair qubit, and she observed the same thing which was there initially in the psi state with Alice. Yeah, just a thing. Yeah, this is the important important point here. Choices of gates by receiver at the Bob's end, is it done in the classical domain or quantum domain? So choices of gates and the application of those gates in quantum domain, and once these gate operations are performed, then only Bob measure the qubit. So see here, maybe. So see here, these first 2 qubits are measured. Third qubit is not measured yet. Third qubit is quantum bit only, and we are applying X gate and Z gate on third qubit. Maybe these are controlled by classical bits, because this after measurement you have this classical bits M1 and M2. Depending upon their value, you are applying X and Z gate. So till now it is quantum information only. When you measure it, you will say, okay, this is the output I am getting, which is same as psi state. Yeah, what is the purpose of the measurement symbol? So see here, on measurement we are getting this two bit of information M1 and M2. If we do not know these values, then we do not know whether to apply X gate or not, whether to apply Z gate or not. Because if you see here, on measure before measurement, this M1 and M2 can be anything, 0, 0, 1 or 1, 0 or 1, 1. It is in superposition of all 4 states 0, 0, 0, 1, 1, 0, and 1, 1. So you do not know what it is, M1 and M2. So for to determine that whether it is 0, 0 or 0, 1, you need to measure them. And once you measure them, suppose if you measure them as a 0, 0, then you know that it is psi 3 is the third qubit is already psi only. So you do not do anything. But suppose if you measure M1 and M2 as 0, 1, then you need to apply X gate so that you can get the psi state, because this 1 and 0 are basically not in proper places. So by applying X gate, you can create exact psi here. By applying Z gate, you can change the sign and you can get the psi state. And in this case, if it is 1, 1, then you need to apply both X and Z gate. So yes, the purpose of measurement is that you need to know whether Bob need to apply X gate and Z gate or not. Depending upon the measurement outcome, Bob will apply X and Z gate on his qubit. Then only he will have exact psi state with him. How many qubits to choose for transmitting from alive to Alice to Bob with one eavesdropper? So here what we are assuming is that there is no eavesdropper. We are just saying that whatever this information, so eavesdropper can be in between, where eavesdroppers can be. So this part is with Alice, Alice private place, and Alice knows this M1 and M2. Just the communication of this M1 and M2, this is classical bits, and these are traveling on classical channels. So in between this M1 and M2 can be knowingly or unknowingly modified. If they are modified, then Bob will not get exact psi state. So eavesdropping or something, some error can happen during the transmission of M1 and M2, because these 2 bits of information needs to be sent through classical channel. So when it is being sent through classical channel, it may be knowingly or unknowingly, maliciously or unintentionally, can be modified. If it is modified, then Bob will not have the same thing. So yes. Yeah. So this has slightly more complex initial state. Okay. So what we are talking about is we are talking about a single qubit state. So single qubit state psi we are assuming as a generic psi state. Just see here. What we have assumed that psi can be alpha times 0 plus beta times 1. So it is a general single qubit state. And in teleportation, we are claiming that we are trying to send the state of this psi, that is alpha and beta, we are teleporting. So single qubit we are teleporting, basically, understand this thing. So single qubit, and this is generic state or general state. So all possible single qubit states can be represented by psi, which has different alpha and betas. So if you change these alpha and betas, then there will be different single qubit states. All we are taking here is a general psi state. So, and we have demonstrated with 0 state and 1 state during our execution of quantum circuit. So in this we have teleported 1 state from this first qubit to third qubit, and also we have shown for 0 also. So means we have demonstrated for 0, we have demonstrated for 1. So this implies that it can be demonstrated for 0 plus 1 state in superposition. Yeah, so I think I have answered. Yeah. Yeah.
Okay, sir. I think you are done, right?
Any other question is there? Then if we have 2-3 minutes, you can ask. If any question is there, participants can ask.
I think participant has wrote down the question and you have given the answer, I think almost all the answer, right? So yeah.
Yes, ma'am.
So we are done. So today's session, thank you very much, sir, for this wonderful talk. And for the participant, all the material will be uploaded on the Canvas. Okay, after the class. And thank you very much, sir. Thank you very much, all.
Thank you, ma'am. Thank you.
Okay.
Thank you, participants.
Yes. So your next session will be on the Wednesday. We will inform you via email
Yes,
also.
Wednesday. Yeah, Wednesday or maybe Thursday, whatever you decide.
Yes.
We can do.
We will email you. Okay. Rajan and Mitra will
Okay.
call. Will coordinate with you.
Okay, ma'am. Okay.
Okay. Thank you very much, sir. Bye.